So we get to visit the last lesson of radical and rational functions. And we're still dealing with the equality idea of zeros, roots, and x-intercepts. Remember, x-intercepts come on graphs. And the zeros of a function or the roots of the corresponding equation are all actually the same number. They're actually the same number. In Physics 20, we studied pendulums and their ability to tell time. Math gives the formula in a slightly different format. It talks about the length in centimeters and the time in seconds. So there's some crossover to physics. We want this girl, Courtney, to build a pendulum that goes back and forth in 1 second. So her time or her period is 1. So 1 equals 0.2 times the square root of the length of her pendulum in centimeters. If we want to employ the x-intercept method, we actually need to change the equation into a y equals or a 0 possibility. So 0 is equal to 0.2 the square root of L minus 1. This is something that you can now graph on your calculator and find the corresponding x-intercept. So I could create that graph by plotting y equals 0.2 the square root of x minus 1 and finding out where that x-intercept is. There are other ways, of course, to solve radical equations, and we should take a look at least one of them. 1 equals 0.2 square root L. For myself, I like to have the square root isolated, so I would go 1 divided by 0.2 is equal to the square root of L. I would figure out what that is. So 1 divided by 0.2 is 5. 5 equals the square root of L. And then square both sides. So 25 would be equal to L, and in this case, 25 centimeters. And my graph should have shown that as well. Another method that people are enjoying is actually plotting 2 graphs. I want to know when y is 1, so I could plot what I'm interested in compared to the equation y equals 0.2 the root of L, and then find my intersection point of those 2 graphs. So now we're back to working with function notation and translations, shifting left and right. State the 0 of the function. The 0 of the function takes place at minus 2. That's a root of x equals minus 2. So to the nearest whole number, find the solution when f at x is 3. My brain is actually thinking when y is 3. So it's going over and it's finding out where 3 is and then reading down. That occurs when x equals 7. I can do something similar here. F at x is equal to 4, and I want to find out when that 4 comes across my path, and that's about there, reading down to about 14. So I found that 14 for C. In D, I'm looking at horizontal shifts of the graph. The graph shifted to the left 6 units. The original graph showed a solution at x equals minus 2, but because of the shift, that new value will be 6 units to the left. So I went minus 2, minus 6. That's going to happen at minus 8. I'm going to try something similar with my 5. I'm going to find out where 5 is on my original graph. So in my original graph, I had a y value of 5 when x was equal to 23. But now I have a shift that is 3 units horizontally towards the right. So I've got to add 3 here. That's not going to happen until 26. Now we get some practice with function notation. I have to take my functions and divide them, so that's kind of fun. 2x minus 3 over x minus 1 minus 5 is equal to 0. So I'm going to need to investigate some algebra. The square root of f at x, so that's the square root of 2x minus 3, is equal to g evaluated at h evaluated at x, which is g evaluated at x plus 5, which is x plus 5 minus 1, which is x plus 4. At least getting that side simplified. Going to change colors to check this one out. F divided by g. So 2x minus 3 over x minus 1. And I want to look at how it's related to x minus 1 over x plus 5. So now we have a combination of rational and radical statements that I have to solve. I'll do a little bit of writing, but I'm going to make my paper longer. So I've increased the length of my paper. I'm going to do that middle one first. I had to bring down the square root of 2x minus 3. My operations tell me I have to square first. So square, square. Actually, I'm allowed to do this graphically. So I'll set this one up algebraically. 2x minus 3 is equal to x squared plus 8x plus 16. Set that equal to 0. That's x squared, pardon me, that 0 equals x squared plus 6x plus 19. Going to try and graph either this one or the originals. Remember, you can graph the original statements and see if there's a solution. So by plotting 2x minus 3 over x minus 1 minus 5, I can make my calculator find the answer by looking for the zeros, and I was able to find the solution to be x to be 0.67. The next one, I like how I've simplified it. Maybe you don't want to do it that way, but take a look at what that graph looks like. By the time I look at the parabola that I've generated, I notice that it's a parabola that does not go through the x-axis. There is no solution because there are no x-intercepts for this one. And the next one, I'm going to create 2 graphs and see where they intersect. So sometimes I'm not sure if I like my calculator and its graphing abilities. The rational graph was pretty gross looking, so now I've considered doing this, making a common denominator, so to speak, or cross multiplying, and I've been able to locate with my graph at least one clear intersection point. I'm going to go second calculate, look for the intersection point, so try to get my graph cursor to be right on top of the intersection point. My calculator does my guessing for me, and I come up with one x value that is suggested 1.72, not quite what was suggested elsewhere. I must admit finding the roots for this one was difficult, plotting in either version 1 or version 2. I actually simplified my statement in hopes of getting something that was easier to read. So 2x squared plus 10x minus 3x minus 15 is equal to x squared minus 2x plus 1. So I get a 0 ability, and I get x squared plus 9x. This is 7x plus another 2 is plus 9x minus 16. And I found the roots of that, or my zeros, using my calculator. And those zeros end up being 10.52 negative and 1.52. The complexity of this graph is challenging. This one I found hard to read as well. But by the time I got here, this was a much easier graph to analyze. So maybe trying to create parabolas is good, but we'll have some fun with this lesson. Thank you.